Hello everyone, I want to talk today about localization and a special form of localization, the so-called Monte Carlo Localization, which is an approach using a particle filter in order to estimate the location and orientation of a mobile platform in the environment. So again, localization is a task of estimating where we are in the world, so where is the system, where it is looking to. And we again are looking into a special variant of this localization problem where we are not restricting ourselves to parametric probability distributions. So if you look into localization using a Kalman filter or an extended Kalman filter, for example, you will be restricted to Gaussian distributions. And that's an assumption that we want to relax today and talk about an alternative way for representing the probability distributions and realizing a base filter in order to estimate the position of a mobile platform. So we want to answer the question, where am I or where is the robot? And we typically assume that we have a map of the environment. Again, we have this underlying map here, like an occupancy grid map, and want to estimate where we are. If you would use a Kalman filter or extended Kalman filter, this would result in a Gaussian distribution describing where the system is. What we want to do today, we want to use particles or so-called samples or pose hypothesis, here indicated by those red dots, which describe me where the system could be. So instead of having one parametric form, we use non-parametric samples as hypotheses where the system might be located. And that's already the key idea of the particle filter. So getting rid of the parametric distribution, turning it into sample-based representation, realizing a base filter, where the particle filter is a form of a base filter, and then realize a localization system with that. So answering this question is the task of today. How do we do this? What do we need to take into account? And what are the principles behind it? So the Gaussian filter, such as the extended Kalman filter or the Kalman filter, will use a Gaussian distribution, so a function of that form, in order to estimate the states under consideration. So in our case, that would be in 2D, the XY location and the orientation, and in 6D, XY, that yaw pitch roll, for example. And we would, or the extended Kalman filter, would use a Gaussian to describe this 3- or 6-dimensional vector. We want to kind of leave the Gaussian world behind today and look for an alternative way for representing this probability distribution. And we want to be as flexible as possible. So we want to estimate or represent arbitrary distribution. So consider we have a function which looks like this. That means we have a kind of high peak over here, but also some kind of plateau of a probability distribution over here. And that may be a distribution that could occur in the real world. And the question is, how can we represent it? How can we describe a function of that form and at the same point in time do efficient state estimation with this? And that's what we want to talk about here today. The key idea is that an arbitrary function, like this function over here, can be approximated with samples. So it means dots which are sitting here at the x-coordinates. Let's say samples that look like this. So these dots, every dot here is a sample, and we can see that in some areas the samples are more densely located, in other areas they are less densely located. And that's already the idea. The amount of particles per area or per unit area describes me how likely it is that the system is there. So every particle is accumulating a little bit of probability mass, and then I'm basically counting how many samples fall into a certain area so that the particle can be seen as an approximation of a probability density function. So again, as a reminder, in the probability density function, you would need to integrate over a certain area in order to obtain the probability mass that the system is within that area. And it's exactly the same thing here we do with samples. We have samples distributed over the state space. Every sample contains a little bit of, or represents a little bit of probability mass. And we simply need to count how many samples fall into a certain region in order to assess the probability that the system is in that region. So that means in areas where the function, or density function is high, we have more samples. In an area where the values are low, we have a smaller number of samples represented. So that's already the idea of representing a function or a PDF using samples. We can go a step further and say maybe we can reduce the number of samples that we need if we weight our samples. So if every sample has a weight associated to that, and the larger the weight, the more probability mass is located in that region. So we have to, of course, have to take care that the weight will sum up to 1, but then, so in this case, it would be uniform weight 1 divided by j, if j is the number of samples, for example. So every sample here would have the same uniform weight j. If we, however, make these samples which are located here larger, so we extend them and give them a higher weight, we may require less samples to represent that function in an appropriate way. So that could look like this. In this case, we have weighted samples. The size of the circle here should indicate the weight of the sample. So in areas with high probability, we have larger samples, and in areas with low probabilities, we have lower samples. So we can see this as representing areas of high probability with either larger samples instead of a larger number of samples. So it's basically the frequency versus weights. So this is a weight representation where areas of high probability are represented with weight, and this is a frequency representation, so to say, where we say the frequency actually matters, how many samples we have there. But it's a very similar thing. It will come back later on the so-called resampling step of the particle filter, but we are mainly using here into weighted samples. So the idea is to use a set of weighted samples to represent a probability distribution. So if we want to represent this PDF about, let's say, the x location of a one-dimensional robot, then we could represent it with this set of samples. Of course, this is only an approximation, because you can see, if you would see this as kind of small Dirac functions sitting here over those weighted samples, and the size of the Dirac function is given by the weight of that sample, or the integral over the Dirac function, to be precise, then this is not a very good approximation of this function, because it will be 0 in this region, high values over here, then 0, high values, 0, high values, and so on. So it's clear that we need to have a sufficient number of samples in order to represent functions well. And it should also become directly clear that this is only an approximation of a function. So the samples are a way for representing function as an approximation. And that's what we're going to use. We will use those weighted samples in order to estimate the belief about the location, position, and orientation of the robot in an environment. Okay, let's look how that sample set looks like, or a particle set looks like. We use a set of weighted samples as our particle set, and every sample has two variables. First is the state hypothesis, so where does this sample think it is located? And this can be a vector, one-dimensional in the example before, or if we are in the two-dimensional world, we may represent x, y, and the orientation, so then this would be a three-dimensional vector. So this guy can be a vector over here, whereas the second variable, the weight, is just a real number. And all the weights need to sum up to 1 in order to have a proper probability distribution, as the integral over a probability distribution must be 1. So, and we have j of those samples. So we have j hypotheses where the system is, and every hypothesis can have a weight. And the larger the weight, the higher the probability that the system is actually located there. And then this sample set represents a belief or a posterior given by the sum of all samples, the weight of that samples, multiplied with the Dirac function centered in the location of the sample. That means this is a weighted sum of Dirac impulses, and at every sample location there's one Dirac impulse. So if I integrate over this function, so integrate over the variable x, the integral over a Dirac function is 1. If our weights are normalized to 1, this will actually give me a probability distribution with an integral of 1, so proper probability distribution. And this is the distribution it actually represents. So it should be clear, again, this is an approximation. We have those Dirac impulses here, and in order to cover or represent a smooth probability function well, we may need a large number of samples. And that's already one of the drawbacks of the particle filter, that we may need to maintain a large number of those samples depending how complex the function is that I want to represent. But the goal is to restrict ourselves to this parametric representation of samples and not restricting the belief, for example, to a Gaussian distribution or a different parametric form. And that's kind of the key idea of the particle filter that we will use for pose estimation in this lecture. Okay, so first have a look how particle approximations of functions may look like. So in this case, we have a Gaussian distribution, for example, this red function over here. Then this is a set of, I think, 200 or 300 samples drawn from that distribution. That means an area where the probability mass is lower, or the density is lower, we have a smaller number of samples, and around the mean, there's a larger number of samples. But we can also use this for functions which are non-Gaussian. So this example over here, it's clearly not a Gaussian distribution. We have more higher density values here and over there to represent the fact that it's more likely to be in a state around that area and is less likely to be outside. So this is a sample-based representation of this function for the red and the blue function. So the question that we obviously have if we start with an initial belief, how do we actually generate samples? How do we obtain those guys over here? How does it work? So the key question is, how do we obtain samples given a function? And the problematic thing in here is that this can be quite tricky. So we cannot easily or in closed form sample from arbitrary functions. There's only a small number of functions from which we can sample in closed form or sample efficiently. Let's restrict this to that. So if we have a uniform distribution, that means every state has the same probability, then it's just our uniform random number generator that we have in our computer. If we have a Gaussian distribution, not every number occurs at the same probability, so I must be closer to the mean to increase the probability that this sample is actually being generated. There are rather simple ways for sampling random number from a Gaussian distribution. Again, this is an approximation. And what you can do is you can just take 12 random numbers and draw values between minus the standard deviation and plus the standard deviation that you want to achieve. So a uniformly drawn number between minus sigma and plus sigma. And you do this 12 times, you add those numbers up and divide the resulting value by 2. Then you will get samples which are actually drawn approximatively from a Gaussian distribution. So you can see from this example, the maximum value that you could draw is sigma. So if you draw sigma 12 times, you will have 12 sigma divided by 2 is 6 sigma. So all the random numbers we can generate lie between plus and minus 6 sigma in this example, which covers already a large area of the probability mass of the Gaussian distribution, but is not exact. So this is probably the most simplest way to draw numbers from a Gaussian distribution. But the question is, how can we do this from other distributions? And there are ways for doing this also for arbitrary distributions. So-called rejection sampling is one of those techniques. We don't want to really dive into the rejection sampling approach here because this is something that we typically can't use in the particle filter setup because it's a very inefficient sampling technique. But what we want to look instead of this is a so-called importance sampling principle. So what the importance sampling principle actually tells us is that we can use a different distribution to generate the samples compared to the function for which I actually want to generate the samples. The only thing I need to compensate for the mistakes that I have done. So let's go to this example over here. Let's assume we want to generate samples from this blue curve over here. This is what we call our target distribution, where we want to estimate our samples from, our target F. But the only thing I can do, I can generate samples from the red curve, which is my proposal function, often called pi. So I assume I can generate samples from pi, but I cannot generate samples from my target F. But what the importance sampling principle tells me is that, hey, you can use your red curve, your proposal, and draw samples from that red curve and get samples that represent the blue curve if you compensate for the mistakes that you have done. And mistake means here the difference in function value between the red curve and the blue curve at a particular function value. So what I need to be able to do for this, I need to be able to draw samples from my proposal distribution, so from the red curve, and I need to be able to pointwise evaluate my target and my proposal distribution, so evaluate the function value for f and pi. But what I don't need to be able to do, I don't need to be able to actually be able to generate functions from f from my blue curve. And what the importance sampling principle tells me is that I need to compute a weight, W, for every sample that I've generated from the red curve, and give it a weight which is the target divided by the proposal. So the function value, so the value of the blue curve, divided by the value of the red curve evaluated at the position x. The only thing I need to take care of is then where, for all locations where the target is larger than 0, so where the blue curve is larger than 0, also the proposal, the red curve, must be larger than 0. Why is this the case? If there would be a place where the target is larger than 0, but the proposal would be 0, there's a 0 probability of generating a sample. So I could never ever generate a sample for that, so I will not be able to approximate f well. You can also see it for the weight computation. If my target would be 0 at a location where f would be larger than 0, I would have a number larger than 0 divided by a number of 0, which gives me an undefined weight on weight. Approaching infinity, that's not something that we want to have. But with this approach, so of drawing samples from the blue curve, that means getting locations on the x-axis here, where the location is determined by the red curve, and then compensate for the error that I haven't drawn from the blue curve by giving them a weight, and the larger this bar over here is, the higher the weight. So in areas where I've drawn little samples, but where the function value of the target is high, I will have higher weighted samples. And in other areas where this is not the case, the weights will be smaller. And so the important thing of the importance sampling principle is we can use a function that we can draw samples from, for example, a Gaussian, in order to generate samples from a distribution which is not a Gaussian, where I cannot sample from in closed form. And this principle is something that is used inside the particle filter in order to perform state estimation. So the particle filter is a state estimation system for dynamic systems, so systems that change their state over time. And the particle filter actually implements a recursive base filter. So the base filter that we have derived in one of the previous lectures, this principle of having a prediction step and a correction step and performing proper state estimation. Compared to the Kalman filter, for example, it is a non-parametric approach. That means it can deal with non-Gaussian distributions, for example, because we don't commit to specific distributions, as we are using samples, as illustrated before, in order to represent our probability functions. Another advantage is, which is not really written down here, is that we have better chances for dealing with non-linear models. So if you remember, the standard Kalman filter required linear models for the motion and for the observation, so for the prediction and for the correction step. And that's something that we do not need here for the particle filter. We can better deal with non-linear functions, and the only thing we need to be able to do is actually generate samples from that, or come up with proposal distributions in order to provide proper samples. And it also has a prediction step and a correction step. The prediction step takes the motion into account. The correction step takes the observation typically into account, and this allows us to realize a base filter. Or under this assumption that we're using the motion model for the prediction and the observation model for our correction step, the particle filter actually realizes a base filter as we have defined it before. One note, of course, the number of samples that you're using determines how good your approximation quality is. So the larger the number of samples, the better you can approximate or represent your probability distributions, so the better your performance in terms of estimation will be. And this brings us to the particle filter algorithm, at least in an informal form shown over here, which basically has 3 steps. The first step is a prediction step, and the second step is the correction step, and we forget about the third step for a moment. And what the first step does, it actually draws sample from my proposal distribution. So it generates a new sample set, drawing samples from the proposal. So where could the system be in? I'm taking my red curve to draw samples from the red curve, although I want to generate samples from the blue curve. And then in the second step, we compensate for this mistake through the application of the importance sampling principle, saying we're taking the target distribution, so the blue curve, and divide it by the proposal from which we have actually generated the samples in order to compensate for the mismatch between the target and the proposal distribution. Speaking in terms of a base filter, we can say if the proposal step is my prediction step, for example, the motion of my platform, then this sampling step corresponds to the prediction step of the base filter. And in this case, the weight, which is computed as the target divided by the proposal, and if I write down the target, write down the proposal, and do some math, it will end up that this will be our observation model that gives me the weight. And this is the correction step, taking into account the observation in order to compensate for the differences. So the analogy between the particle filter and the base filter comes from using the prediction step and the prediction or the motion model and the observation model for the sampling step, for the proposal, and then for the weight computation. But it's all based on the importance sampling principle and automatically comes out of this if we put in the right proposal. It should be noted over here that we as a user can define this proposal distribution. So it's up to us, as long as we are in line with the importance sampling principle, to choose this. So we are allowed to choose the motion model, for example, of a mobile robot performing localization and describing the motion of the platform. We are allowed to do that because this is a user-defined choice. But this is a user-defined choice, and then the weight is not a user-defined choice anymore. It results from how we select the proposal. The third step is a little bit of a tricky step, which maybe is not intuitive in the beginning. It's a so-called resampling step. What this step does, it basically draws samples from our sample set, from our weighted sample set, with replacement. And it does it in a way that we draw a sample I with probability W of I. So the probability that we draw the sample I is the weight of that sample. And we repeat this process j times. So that means we have our sample set, we draw a sample randomly from that set, and the probability of drawing that sample is proportional to its weight. So the higher the weight, the higher the probability that we draw it. Then we look at that sample, we make a copy of that sample, let's say put it to another bucket, and put the original sample back to the original set. And we repeat this process j times, so that we get j new samples in our resampled bucket. And the weights in this resampled bucket we all set to 1 divided by j, so they have all uniform weights. So what we are doing here is we are basically replacing weights by frequencies. So we're taking the weighted samples and turning them into uniformly weighted samples. By having a higher probability of drawing samples with a higher weight, and this form replicating them, duplicating them. And this generates me a new sample set which represents still the same distribution, but replaces the weights by frequencies. And I do that because I typically have only a finite number of samples if I'm implementing a particle filter. If I have a finite number of samples for representing particles, that means at some point in time there will be samples which, let's say, go into areas of my state space which have a very, very low probability, maybe even a probability of 0. So these particles with a very low weight do not contribute a lot to approximating the probability distribution well. So they have a very, very small contribution to representing the overall probability mass. So it's better to take that sample out, eliminate it, and replace it with a sample that is in an area of high probability. In this way, we are taking our memory in a smarter way by saying we are using our memory for areas of high probability. And that's basically what the resampling step does. So if we would have an infinite amount of memory, we could completely ignore that step. But in most cases, or in all real computers, we only have a finite amount of memory for representing our samples. And therefore, this resampling step makes sense because it kind of shifts the particles into areas of high probability without changing the distribution itself. So that was kind of the informal particle filter algorithm with its 3 steps. We can only look to the more formal description of an algorithm, which would look like this. So we have a particle filter, which has the sample set representing the belief of my system at time t-1, my current motion command, and my current observation. And then what I'm doing is I have my sample set. So my predicted sample set is and my new sample set are equal to the empty set. So I start with kind of 2 empty buckets. One I will use for the prediction and one I will use for the correction. And then I'm sampling samples from my proposal distribution. And again, this pi is user-defined choice. So what's a hypothesis where the state can be in? And this, of course, depends on my previous belief. So this previous belief will be sitting somewhere in this proposal distribution. And in most cases, also the motion or the motion command will be sitting here because it will tell us how the system will evolve from the previous point in time to the next point in time. And then the next step for that sample is the weighting step, taking my target distribution divided by my proposal distribution. And here typically I have to sit down and do some math and write down how that actually looks like. And in most of the cases, this will lead, at least if you follow using the motion model over here for my proposal, will lead to an observation model, a weight that is proportional to an observation model in order to write that down. So I can compute my weight. And then I add my weighted sample set as my new temporary sample set, x bar over here. And I'm just repeating this and adding this. So up to the step here, if I went through the whole loop, I basically do my prediction step and my correction step at the same point in time. So I will have a sample set x bar, which is my temporary sample set. So it's not really the predicted sample set that I said before. It's my temporary sample set. Let's better call it like this, which contains all the samples drawn and reweighted. And then the last part over here is my resampling step. So I'm repeating a process j times. I'm drawing j samples with the probability proportional to the weight that I've just computed, and add that drawn sample without a weight to my new sample set, or with uniform weight to my new sample set. So as a result of this, I have at that point in time a sample set xt, which represents my belief at time t, having uniform weight and having replaced the weights by frequencies. And then I'm repeating this process for the next observation, next control command coming in. And this is the general particle filter algorithm, where we as the user have to define the proposal distribution and then derive how target divided by proposal looks like in order to compute the weight in an appropriate way. If we would be able to draw from the target distribution itself, that would be trivial. We would just need to draw those samples. There would be no weight, and then also I can skip the resampling step, because then all samples would have the same weight. So if we could draw directly from our target, the whole steps wouldn't be needed. We could just represent our target distribution with samples. In practice, however, that is often not the case. We cannot sample from our target. We can only sample from a proposal, which covers typically parts of the target distribution, and then need to be able to compute a weight in order to account for the discrepancy. The key thing is that for the target, I only need to be able to evaluate pointwise, so add a sample location, and I don't need to be able to draw samples from this. And evaluating a function, so computing f of x, is easier than sampling from a function. And therefore, this is a prominent and effective algorithm for performing state estimation. So far, I mainly looked into the general particle filter algorithm and introduced it in, let's say, informal way, using the important sampling principles and relating them to the idea of the recursive base filter. The next thing we want to do is look into Monte Carlo localization. With Monte Carlo localization, we refer to as estimating the position and orientation of a platform using a particle filter. So it's robot localization using a particle filter, and this is something that we typically call Monte Carlo localization. So in our 1D examples, you have seen this plot a few times. If we have a robot which sits over here and it has this sensor which only tells them, can only detect doors and tells the robot you're in front of a door. When you're in front of a door, the robot drives around. So I've seen this plot a few times. Then you will end up with a belief, hopefully, that concentrates a large number of samples over here where the system actually is. There are some remaining samples over here, which could be explained by having a door observation over here, and then the second door observation was a false observation. So some of the samples survived here, but the majority of probability mass actually sits over here. Also, in this example that I've shown before, where am I generating those samples? That's the question I want to answer with Monte Carlo localization. Generating those sample sets, but also then maintaining them and updating them based on motion and based on observations that we are obtaining. Just an example how that could look like. So what you see here is a belief where all the particles are spread all over the place. This is kind of a uniform distribution, randomly sampled over the space where the system can be in. And then if the robot drives around, obtains observations, generates motion commands, we can start to focus our beliefs. So the particle cloud will evolve. Some particles will die out when they can't be well explained by the observation, and the probability mass concentrates in several places. And this is because the environment is at least to some degree symmetric. And so you will have multiple hypotheses that may remain. Again, something that you cannot do well with the Gaussian distribution. Also, this cannot be represented well with the Gaussian. At some point in time, your system will converge, and you will actually end up with a belief that is similar to a Gaussian distribution. So just to come back and make this point very clear, what the particle filter does, it takes a sample as a pose hypothesis. And every hypothesis says, that's where the platform is. And then it has a weight, kind of a term of fitness, or how much we can trust that particle, which tells us how likely that is. And by not having one hypothesis where I am, but a large number, 1,000, 10,000, 100,000 samples, we actually obtain a belief, a set of possibilities where we are, and this set of possibilities describes my probability distribution. But every particle itself says, I did the right job, I know where I am, I have my state estimate X, and I have a certain weight associated to myself. So in the view of the particle, it did the right job and everyone else was wrong. And only through using a lot of those hypotheses, we actually get our belief. That's kind of an important thing that is worth considering when you think about that particle filter. So what we do in Monte Carlo localization is we say every particle represents the pose hypothesis. So if you're living in a 2D world, this would be an x coordinate, a y coordinate, and an orientation angle, theta, representing the yaw of that platform. Or if it would be in the 3D world, this could be x, y, and z, yaw, pitch, roll. Or maybe I have a car driving an environment that maybe just x, y, z location, and maybe the yaw orientation, because the roll and pitch angles may be always very small and may not be one to estimate that in a particle filter. So the dimension that I need to estimate defines the state vector of every particle, so the dimensionality of that sample. And then in Monte Carlo localization, we use our motion model as our prediction step. So we say, where have we been at the previous point in time? So this is information which comes from the recursive belief. We use our odometry command or motion command and estimate where we are. And this is what I use to generate new samples. So if I'm a sample, for example, within a particle filter or in a sample set of size t-1, and the motion command said, you've driven a meter forward, what I would do here, I would take my position and move it a meter forward, or at least approximatively a meter forward. Why approximatively? Because I'm sampling from this distribution. And if my motion has noise associated to that, which is always the case in reality, I will not maybe move the particle 1 meter forward, but maybe 99 centimeters, or a meter 2, or a meter 3. So for every sample, we draw from this distribution. We don't take the maximum value, we draw from this distribution, so that some samples move forward 1 meter, some sample moves forward 80 centimeters, some sample moves forward 1 meter 20, and so on and so forth. So we are generating a new set where we are increasing the uncertainty. We are spreading out the particles in the world about the predicted belief, because we add uncertainty to the world if we only move through the environment without observing it. And the second step, and this is the result from this choice. So this is a user-defined choice that we do in Monte Carlo localization. And as a result from this, if you sit down with the math, write down the target distribution, write down the proposal, do some math, you will get a term which is proportional to my observation model. So what's the likelihood of obtaining an observation given we know where we are and given we have the map of the environment? And we only need that proportionally because later on we anyway will normalize our weights to 1, and therefore this I only need to know it up to a normalization constant. And this results from this design choice. If we would choose a different model over here, then we would end up with a different weighted term over here. But if we choose the motion model as a proposal, we will end up with the observation model as our weight for every sample. And again, so what we are doing, for every sample we generate this pose, we generate a new hypothesis by moving it forward. And then in the second step, in the weighting step, we are evaluating how likely it is to obtain the observation that we actually got, assuming we have been in that place of that particle. And here some beauty comes into the game. A particle is a single pose hypothesis without uncertainty. So I can really evaluate my model saying, given I'm exactly here, how likely is to obtain my observation? And if you think back, this was exactly how we computed our observation model in one of the previous lectures. And so by having this given state, so this given xt, we can just use the particle position itself because the particle believes it did the right job. So it is given, we can very easily compute this observation model because we assume we know where we are, we know what the world looks like, and then we get exactly the likelihood of obtaining the observation that we had before. So it's the evaluation of my observation model as we have explained it in the previous lectures. So turning the particle filter algorithm into a particle filter for localization, so MCL, the only thing we need to change are those two lines. So we are defining our proposal distribution as the motion model, and this then results in being the observation model in our weighting step. And what we also need to take into account, which is not really written in here, that the dimensionality of this xt, so of the sample itself, is the xy yaw or xyz yaw pitch roll position of my platform in the environment. Okay, and that's it. The rest stays exactly the same. Standard out-of-the-box particle filter algorithm. I only plugged in my motion model and my observation model in here. So as an illustration, how does it look like? So consider we start with our MCL example over here. So consider we have a robot somewhere in the world standing currently in front of the door, and this is our uniform distribution, our random sample set that we have initialized in order to represent our state in this kind of one-dimensional world. So if you then perform the correction step, so this is our observation model, so we get a return, a peak in front of every door because the sensor said, robot, you're in front of a door. Again, there's a certain probability that this may be wrong, therefore we have non-zero probabilities here, but it's a higher probability that we're in front of that door. So the weighting step will then increase the weight of those samples which are at that locations. So these samples would get very, very high weights, and the other samples will get low weights. So this is my new weighted sample set representation. Okay, so I'm just taking this over here, copy it up, and do the next step. So this is just copy-paste from the previous slide. The next thing I do my resampling step. That means I'm replacing weights by frequencies. So samples which have been located over here, I duplicate them, put them down here, and those are less likely to be chosen. Because if you just copy the samples and increase the frequency at the same location, you actually won't see it in the plot. So what this plot shows is the resampling step and the motion prediction step. And by moving the particles forward and spreading them due to the sampling process, you see this density increasing here in this illustration. So of course, these are kind of two steps done in one, but there's something that you often see in particle filter applications, because otherwise you don't really see that effect in the resampling step where the samples get condensed in certain locations. And then, again, we repeat the process. So copy this part over here, and then integrate the next observation. So copy this over here. The robot is again in front of a door, sees a door, so we have this observation function. And now we can see there's a smaller number of samples over here, because this was just a few samples which kind of those guys which survived over here, which get a weight over here. But the majority of samples sits actually in here. And so they get very, very high weight. And those samples get a really high weight. And we have, again, a few of them sitting over here. So in the next resampling step, those will be replicated dramatically more often than all the other samples. A few of those as well, but most of the others are likely to die out. And then integrating the prediction step of the next motion, I will see that the majority of samples will be distributed over here, representing the position of the platform. So again, have a small animation. This is an animation done by Dieter Fox of a mobile robot navigating in an environment. And this is actually a technique that has been developed a bit more than 20 years ago with substantial contributions here from the University of Bonn. So what you see here is actually a floor plan of an old building in Bonn, a building which has probably been taken down or will be taken down soon, the old computer science building before they moved here on campus. And this was a corridor environment, and you can see this was the actual trajectory that the robot will take, and you will see the animation in a few seconds, how the robot moves through the environment. The important thing in here is that this is a symmetric environment. So except of kind of a few things which are in the rooms, located in the rooms, you can flip it the other way around and the corridor would look exactly the same. So as the robot moves through the corridor, you will actually see that multiple hypotheses, in the end 2 hypotheses survive, and only by moving into a room, the robot is able to identify where it actually is. So let's see how it looks like. So what you see is this dot here shows the current best estimate where the system is in. These are the observations, which are in this case sonar observations. And you will see this position jumping around a little bit in the beginning because the system doesn't know where the robot actually is. It has a multimodal belief and it's jumping around until it actually converges. So Oops, sorry, to start that video. Okay. So what you see here, the system is moving. A lot of probability mass concentrates in the corridor. And if I kind of pause that video over here, you can see that a lot of the probability mass is accumulated within the corridors through this repeated sampling, weighting and resampling step. A few samples have survived over here, but there's nearly no samples in the other rooms. And you can also see that there are two clouds. Those clouds are very prominent. These are kind of two explanations where the system could be, because they represent the symmetry of the environment. So if I then can continue and let the system, the animation continue, you see some samples will survive over here, which is the most likely pose, but also a significant number, oh no, sorry, this one, survives over here. And only by moving into the room, because those two rooms look different, the system is able to identify that it's actually here and is not located over here. So this cloud will die out, and this is a cloud which actually survives. So I can actually show that video again, now also in full screen mode, where you can see how the system estimates the position of the platform recursively, taking into account motion, observation, and resampling, moving through the corridor, then turning around. We see that the two hypotheses survive before the system enters one of the rooms and then is able to identify where the system is located and which hypothesis is probably wrong, and then has converged to a unimodal belief. But in order to end up there, we need to have the ability to represent multimodal distributions. Okay, last but not least, I want to have a look into the resampling step. So again, resampling was this kind of third step which says replace unlikely samples with more likely ones, because we don't want to spend too much memory on areas that don't matter. And this was this resampling step. It's basically drawing samples proportional to their weight with replacement and doing this j times. And you can see this as kind of a mathematically motivated survival of the fittest approach, where the bad samples die out and the good samples get replaced. And again, this is just a trick to get the samples move into the more likely areas of the state space without changing the belief, or only doing minor changes to the belief. And this is needed because we only have a finite number of samples and cannot represent an arbitrary number of samples. So how does this resampling work? From the way it is described here, draw samples by replacement, that sounds very easy. And it's something which is often called roulette wheel sampling. Why is this the case? Because you can envision a roulette wheel where the buckets of that roulette wheel represent the weight of the particles. So the larger a bucket is, the more likely that this sample is actually going to be. So if you want to draw a sample, you just take your ball, put into your roulette wheel, and see where the ball ends up, in which bucket. And if you have a larger bucket, the ball is more likely to end up there. And so how you can do this, you basically have your weights, they're normalized to 1, you draw a random number between 0 and 1, and then determine the bucket where you end up. So you would draw a sample. In this case, you end up being here. So you draw a number, let's say this would be approximatively 0.22, and you will end up in the weight of particle number 3. And you repeat the process, you have a number drawn close to 1, so you end up drawing particle Wj, or the jth particle, for example, and you repeat this process over and over again, drawing those samples, and in this way you can generate the new sample set drawing by replacement. And all the samples that you have drawn, you copy, so the state of particle number 3, the state of particle number j, and the state of this particle, for example. And this is what we call roulette wheel sampling. It's the simplest form of sampling. And you can actually do this in an efficient manner by, you have to do it j times because you're sampling j times, and you need to find which bucket the ball ends up with. And that's something that you can realize with binary search, because you know that the sum of the weights is 1, and you're basically looking in which bucket you're ending up with if you would accumulate those buckets or cumulative weights. So you just need to do a binary search in an array, which you can do in log j times because your array has j entries, so that we end up with a computational complexity of O of j log j. And this is a standard roulette wheel sampling. They also have an alternative way to do this, and as we'll see in a second, a better way for doing this. And this is the so-called low variance resampling, also called stochastic universal resampling. Here the idea is we have a modified roulette wheel, so we still have our roulette wheel, and instead of a ball, we kind of see this as an error, which is, and you're basically turning and depending where the error points to in the end, that's the bucket that is chosen. Except of one arrow that we have been using over here, we are using now n arrows, and they are distributed with an equal spacing in the angular space. So if I have 8 arrows between all arrows, there is a difference of 45 degrees, for example. And then, these are my arrows, and I'm just turning those arrows once, and then where all the arrows end up, these are the samples that I'm choosing. So if I basically just draw one random number and not j random numbers, and then all the other samples are deterministically determined. And so if you draw, this is basically how a draw of a full sample set looks like. And that's something which is called stochastic universal resampling, or also low variance resampling. And it has a few advantages, actually 2 advantages. The first advantage is that it is faster to do. You can do it in linear time, because you only draw one random number, basically determines where the first arrow pointing to, and then you just, while walking through your array, you determine where do the other arrows end up, because you know those arrows have an equal spacing. And you don't need to realize a binary search is just one pass through an array, which you then can do in linear time, because you're basically doing the drawing not one after the other, you're doing the drawing at the same point in time while you're moving through the array. So the move through the array is a bit more expensive, but you only have to do it once and not j times. So this is a lower computational complexity. This is nice, but this is typically not the factor why stochastic universal resampling is superior to standard resampling. That's a different reason. In order to do that, why standard roulette wheel resampling can be suboptimal is the following. So consider you're doing a sampling with replacement. So you sample and you put your sample back, and then you do that again. And this can lead to results where the output is suboptimal. And the output, or the idea, let's say that way, behind resampling was to eliminate samples which are in low areas of the state space and represent them by samples which have a high weight, which are more likely to happen. And if I ask yourself the question, what actually happens if all samples have exactly the same weight? What's going to happen? Let's say our sensor is really, really bad. It doesn't provide us any information, so all samples will have the same weight. What happens? I'm actually generating samples. The observation doesn't tell me anything, so all samples will have the same weight. And then the resampling step kicks in, and it draws random samples and duplicates them, if they've drawn them multiple times or 2 times. And other samples will not be drawn and will die. So state hypothesis will basically die out, and others will be duplicated or even exist multiple times. So in the next time step, all the samples have been replicated and others have died, although no sample was better than the other. And if we now repeat this process over and over again, because our sensor has been blinded, for example, our camera is dirty, someone is standing in front of our laser scanner, whatever it is, we don't get good observations in, then this resampling step would even enhance this process. So before I had one sample, for example, just duplicated, now drawing the sample is again increased in probability, so it will be drawn more often, and then we have 4 or 8 times this sample, and other samples will die out. So if all particles have the same weight, there's actually no way that we should choose one, or it doesn't make sense to choose one particle over another. So in this situation, the stochastic universal resampling or low variance resampling will actually reproduce the same sample set over and over again. So if our sample set or our weight is not very good to determine which samples should be replicated, which samples should be eliminated, standard red wheel resampling will hurt our belief, while stochastic universal resampling will not. And therefore, we will always choose stochastic universal resampling, because it's faster and it is better for us. So how would we implement that? We can actually implement this quite efficiently. So consider that we have our particle set, and the size of these are kind of basically the unfolded roulette wheel in this example. I draw the first random number, and then I want to advance to the next sample in a distance of 1 divided by n. So I basically have a space 1 divided by j, a spacing of 1 divided by j, and I'm basically picking the buckets where the arrow is pointing to. This is basically the unwrapped roulette wheel, turning the wheel into a straight line. So the first thing I do, I pick a random number between 0 and 1 divided by j, and then I pick j minus 1 times the particle in 1 divided by j steps walking through my array. So how do I implement this efficiently? I can implement this efficiently by building an array which has j elements and always stores the sum of the weights. So the first bucket has the weight of particle number 1, the second bucket has a sum of the weight of particle 1 and particle 2, the third bucket has a sum of particle 1, 2, 3, and so on. The last bucket gives me 1 because my sample set is normalized to 1. What I then do, I draw a random number between 0 and 1, which tells me which bucket do I start with. And I'm basically comparing, is this random number smaller than W1? If it is smaller, I know the error sits in bucket number 1, and I say, okay, perfect, take bucket number 1. If this is not the case, if it is larger than W1, that means I'm actually sitting over here, so the first particle at a very small weight, and so I should choose particle number 2 as the first weight. And then I'm repeating this process, advancing this weight 1 divided by j steps, further and further, and in order to estimate where I end up with. So I basically have 2 loops, a for loop, because I'm doing this j times, the overall thing j times. And I'm having an indicator tell me where this arrow points to, which is my u, which is my initial random number, plus the index of my sample that I've chosen times 1 divided by j. So this is a spacing. And I'm basically moving further, checking which bucket I'm in, while my u is larger than the cumulative sum of this array. So this is a cumulative sum. And once this is smaller, I pick the particle. And I'm repeating this step, and exactly j particles will be picked. So I can do sampling with replacement in a very efficient way using this idea. We can also write this down as a more formal algorithm. So we start with a random number between 0 and 1 divided by j. I have my cumulative array, which I also kind of actually build up. I don't even need to compute it explicitly. I kind of just need to maintain the variable of the current bucket where I'm in. I'm iterating j steps, and this is basically copied from the previous slide. So u is the indicator which sample I'm choosing, and then while u is larger than the current position in my cumulative array, I'm jumping to the next bucket, compute the next value of the cumulative array, and repeat this until this is not the case anymore. I pick my sample and I continue. And in this way, I'm drawing j samples in a stochastic universal resampling way. So low variance resampling or stochastic universal resampling is an alternative way that keeps the sample set the same in case of identical weights of the particles. And of course, we typically don't have identical weights, but we may have weights which don't differ much. And even if they don't differ much, the variation that this low variance resampling brings in is actually minimized. In addition to that, it's faster to compute, so there's really no way for using roulette wheel sampling. Always use stochastic universal resampling. That's the take-home message over here. And now we actually have explained all the parts of the particle filter. You know how the particle filter looks like, you know how resampling looks like, you know how to draw samples from simple distributions such as a Gaussian. The only thing you need to put in at the user is actually your motion model and your observation model. And we have defined a few in the previous lectures so that you can use them, for example, for a wheeled mobile robot equipped with a laser scanner. And I want to show a few examples of MCL in action over here. And I want to start with a slide showing the first robots that actually used Monte Carlo localization. This was the robot Rhino, actually here developed in Bonn. Minerva, which was kind of a similar platform, let's say that way, also used as a museum tour guide, and then later on the robot Albert in Freiburg, which we have been kind of 3 robots which have made Monte Carlo localization popular, which again, initial developments have happened here in Bonn and then in Carnegie Mellon University and later on in Freiburg, building the particle filter based localization into kind of the gold standard of localization, at least for indoor localization of mobile robots today, and especially if you need to maintain multimodal beliefs, this is really the standard approach. And I want to show some kind of old slides which show how the robot Minerva, which was this one over here, drove for a period of, I think, 6 weeks in the late 90s through the Smithsonian Museum of American History, giving tour guides, tours, acting as a tour guide, giving tours to visitors, driving around. And there was also an event where the same thing happened here in parallel in the Deutsche Museum in Munich as well as in here in Bonn. At that time, Rhino was here in Bonn. and while driving around performing localization tasks, interacting with visitors. So this is a floor plan here of the Smithsonian Museum of American History, or this one section where the robot Minerva was installed. And you can see here our sample set distributed over the space. The robot was equipped with 2 laser rangefinders, so one looking to the front, one looking to the back, which is here illustrated by those blue dashed lines. So this was a sample set. A first observation was actually obtained, and this always shows you kind of where the system thinks right now it is. It's not the right place. In reality, the system is over here. We integrate, from a resampling step, integrate a motion command, and then in the next step, the particle set looks like this. So we have a few positions over here where the system could be. We can see denser particle clouds also down here and down here are 2 areas which share some similarities and could also explain the observation better than other approaches. Then we can again put in our observation, and what is probably a bit hard to see here in the video, but if you look to the slides, you will see it better. You see some of those samples being in dark red and the other one bright red. And so the darker the color, the higher the weight of that sample. We can already see here that probability mass has converged really well to the right location. We integrate the observation, re-rating our samples, and then performing the resampling steps. So you can see between this step and this step, weight update and resampling, you see that some of the samples are actually dying out here in this unlikely regions of the state space, for example. And then the next motion is incorporated here. The motion was very noisy of that platform. You can see the particle cloud spreads out quite a lot. So we get the new observation in. You can see again that the measurement is obtained and is compared to the sample set. You can see that here in dark red, the weight update is performed. So the samples here in the center get a higher weight than outside. The resampling is performed. You can see here unlikely state space in the outer regions as well as in other areas will die out, and then the motion update is performed. We get a new observation. We perform the weight update with the resampling, and this way the system can move through the environment and estimate and track its pose over time. And this was kind of one of the first animations of this Monte Carlo localization, which has been successfully used for extended periods of time in populated scenes. There are 2 other examples I want to show where the system has been used. So one is in a production hall at KUKA, which is a German robot manufacturer, of a robot driving around performing logistics tasks equipped with laser scanners, localizing itself in a map while doing construction tasks. You can't do this only indoors, you can also do it outdoors. So this is an outdoor traversal of a robot navigating here on a graph-like or combined graph grid-based map, driving here around. And we can see those red dots over here, not the samples. This is kind of the overlay of the current laser scan with the position of the best particle. The cloud is actually here so small that it's actually hard to see that because the system, when you optimize your models, you get really precise motion estimates and can track your position really accurately over time and come up with good estimates and use this to steer your robot even in outside environments, dynamic environments, and it's a very versatile technique for performing robot localization. The particle filter, however, has also some disadvantages. Not everything is great. So one of the problematic things in here is if we have high-dimensional state spaces. Why is this the case? Because we need to cover our state spaces sufficiently well with samples in order to represent the probability distribution. So especially if we have 10-dimensional state spaces or 20-dimensional state spaces, the particle filters typically will not work well. So the particle filter works well in low-dimensional spaces, or if the uncertainty is not too huge so that we can actually represent the space of possibilities in an efficient manner. And actually the number of samples that you need grows exponentially with the dimensionality of your state space. So in 2 dimensions, no problem at all. 3-dimensional state spaces get already more tricky, but it's still fine. 4 may still be okay, but higher than 4, you need to have sufficient computational resources in order to estimate the position of the particle well, or you need to apply tricks to kind of restrict the size of your particle cloud for not being required to use millions or hundreds of thousands of particles. So it depends always how many assumptions you can make about your environment, how many things can you simplify, but in areas where you have high-dimensional state spaces or regions of very high uncertainty, then the particle filter may be problematic, and so that's something that you need to take into account. If you have a too small number of samples, you may suffer from the so-called particle depletion problem, that particles die out and leave the likely areas of the state space because your model is, for example, too focused in comparison to the number of samples that you're using, and so your filter will diverge at some point in time. So these are some of the problems of the particle filter. It also has advantages. It's one of the few approaches which can handle non-Gaussian distributions very well. Other non-parametric approaches can, of course, handle also non-Gaussian distributions, but they also suffer from certain problems like an exponentially growing memory requirement for depending on your state space, which can be tricky. So the good things is it really works well in low-dimensional spaces. It can be also used to very elegantly handle data association ambiguities because you can make own data associations for every particle. So every particle can, because it has no uncertainty associated to this, you can very easily do particle-dependent decisions and see which particle survives, which does the best estimation job, and this way incorporate additional knowledge very easily into those particles. You can also easily integrate multiple sensing modalities by just multiplying the weight with the weight computed from another sensor, so that can be very easily done. It's also comparably robust, so even if you do some mistakes, your models are not the perfect models, your particle filter will actually compute quite good beliefs, and even in suboptimal setups perform quite robustly, and it's furthermore very easy to implement. So you suffer from a very small number of problems that you may have, especially numerical issues. If you look into a Kalman filter, for example, that can be more tricky. The particle filter has less issues that you typically need to deal with. We also should say that there are several variants of the particle filters to eliminate some of the drawbacks that are out there. For example, there are variants of the particle filter for real-time estimation, like real-time particle filters that can also handle situations where the sensor data comes in at different frame rates, which need to appropriately be taken into account. Delayed state space filters, when some of the streams come in very late and need to be resynchronized, or Rao-Blackwellized particle filters. If you're working in high-dimensional state spaces, and you can split up the state space and a part of the state that you can estimate with samples and part which you can then compute it conditioned on those sampled beliefs, you can do things in a more efficient way. So the Rao-Blackwellized particle filters have, for example, been used for addressing the simultaneous localization mapping problem when you need to localize a robot and build a map at the same point in time, and have led to very successful mapping algorithms there. Although the dimensionality of the overall problem goes into the millions, but there's only a small number of them that you need to represent with samples, and then you can compute the rest analytically. So in sum, particle filters are a recursive implementation, or a recursive base filter, a variant or an implementation of a recursive base filter that can deal with non-parametric distributions. As you also have seen, we haven't made any assumptions about linearity of models. So motion models can be non-linear as long as I can sample from them, which can also be an advantage that I can represent, for example, my banana-shaped distributions very well. What we're doing, we are representing our belief by a set of samples, and every sample says, I did the right job, everyone else was wrong, and that's where I am, or that's what the state looks like. And through a collection of those samples, we are representing probability density functions, and this way can represent beliefs, for example, about the position of the robot. We typically draw samples from a proposal distribution that takes the belief at the current point in time and advances it to the belief at the next point in time. And in order to account for the fact that the proposal distribution is not the target that I want to estimate, I need to take the difference into account through a weight which is given by the target divided by the proposal distribution. So if you implement your own particle filter and use it for a real-world system, you need to make sure you have appropriate motion and sensor models. Of course, if you screw up your motion and your sensor model, which are the user-defined choices in here, then your system will not estimate, will not do a good job in estimating your state. But if you do that well, the particle filter is a very robust technique. And we have used this here to illustrate Monte Carlo localization, which is applying the particle filter for localizing a robot. That means every particle represents a possible location and orientation of our platform, for example, X, Y, and yaw. And then we use our motion model as a proposal distribution for advancing the particles, and as a result of this, using the observation model for computing the weights. and this is something which is called Monte Carlo localization, and is today one of the standard choices for performing mobile robot localization, especially if you're indoors, if you have to deal with multimodal beliefs and cannot rely on external sources which kind of restrict your estimate to a small number of hypotheses or even a single hypothesis, so that you can use a Kalman filter, for example, for the estimation technique. So MCL is one of the standard algorithms and a choice to the standard choice, and also have kind of the test of time has proven that within the last 20 years that MCL is a very robust and efficient localization technique for mobile robots. If you want to dive a little bit deeper or look into literature, I recommend the Probabilistic Robotics book. 3 tackles the particle filter, and chapter 8.3 addresses Monte Carlo localization as the realization of the base filter using a particle filter. And for that, what you need to know is your motion and your observation model. So you need to rehearse chapter 4 and 5 if you forgot about that, because you will need a way to describe the motion in a probabilistic sense and sample from that model, and you will need to be able to evaluate your observation model pointwise, so estimate for a certain location what is the likelihood of obtaining the observation that I got given that I'm at that place, which is what the observation model does. If you put all that together and apply the standard Monte Carlo localization algorithm, then you can estimate and track the position of your platform over time. That's it from my side. Thank you very much for your attention, and I hope you learned something about how to estimate where your system is in the world, even under multimodal beliefs. Thank you very much for your attention.